up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we start a new unit on exponential and logarithmic functions. Today, with the first section of our notes, we're going to be taking a look at exponential functions. So if you have the notes printed out from Google Classroom, you can follow along there. If not, go ahead and add these notes to your running notebook. We're going to focus on this lesson on graphing the exponential function. But before we do, we want to actually take a look at some reviewing some exponential properties, something we focused on earlier this year that we want to make sure we're fresh on before we get into exponential functions. So the definition of an exponential function, and this notation may look familiar, is any function of the form b to the x power. So our variable is in the exponent. And this is where the base b is going to be greater than 0, not equal to 1. And our variable x is assumed to be a real number. So this form, this b to the x power form, should be familiar. Now, just to kind of refresh some of our properties, we're going to deal with some variables. A is greater than 0. A, B, R, and S are all real numbers here. Recall that any base, when you multiply any base that is the same, their exponents are going to be added. When you take a base with an exponent to another power, those exponents are going to be multiplied. A negative exponent takes the reciprocal of a fraction, or the reciprocal of a base. So if I have b over a to the negative r power, getting rid of the negative would give me a over b, the reciprocal of the fraction to the r power, which I could then write as a to the r over b to the r. Remember, when dividing the bases that are the same, we subtract the exponents. And when you have the multiplication of two different bases, in this case a and b, to a power, you can essentially distribute that power to each of the terms. So this would be a to the r power and b to the r power. And finally, if you have a fraction or a rational exponent, that rational exponent is the same as creating a form of a root. So b to the r over s power. S, the denominator, would become the index of the root, so this would be the s root, to the r power. The power can be inside the radicand, or inside the radical expression with the radicand, or outside. Either or is okay. So all of those are familiar properties that we're going to need to use. So just kind of as a refresher in problem number 1, it says to evaluate each of the following expressions for x equals 2, x equals negative 1, and x equals 1/2. And then we can check our answers with the calculator. So starting with x equals 2, let's go to problem A, where we're given f of x. We're going to find f of 2, which would be substituting 2 in for x, and 4 squared we know here is 16. So we can check that on the calculator. 4 to the second power would be 16, 4 times 4. F to the f of negative 1, so our next x value is negative 1, would be 4 to the negative first power. And we know that 4 to the negative first power would take the reciprocal of 4, and this would be 1 over 4. Again, we can check that in the calculator. The calculator is going to give it to me as a decimal, but I can convert that to a fraction and see that it is, in fact, 1 over 4. F of 1/2 would be 4 to the 1/2 power. This would be a rational expression. The denominator is 2, so this would create the square root of 4 to the first power. We know the square root of 4 is 2. So again, we can check that in the calculator as well. See if you can pause the video for just a moment and find g of 2, g of negative 1, and g of 1/2. Hopefully you got a chance to work through each of those. So if we're going to find g of 2, this would be 4 over 9 to the second power, which would be the same as 4 to the second power over 9 to the second power, or 16 over 81. Again, if we were to check that in the calculator, when you type that into the calculator, you want to make sure that you put the 4 over 9 in parentheses, and it's going to give us a decimal, and we're going to convert that to a fraction, which is 16 over 81. Then g of negative 1 would be 4 over 9 to the negative first power. The first power isn't going to change the bases, but the negatives will. It would create the reciprocal of 4 over 9. And this would be 9 over 4. Again, here I had a mistake there, but again, if we check that in the calculator, it's going to give us a decimal, which I can convert to a fraction, and we would see that that is, in fact, 9 over 4. Then g of 1/2 would be 4 over 9 to the 1/2 power, which would essentially be taking the 1/2 power of 4 over the 1/2 power of 9. And we remember that the power, the 1/2 power is a square root. So this is the square root of 4 over the square root of 9, which would become 2 over 3. Now, you didn't necessarily have to write out all the steps the same way that I did, but as we can see in the calculator, and when we convert it to a fraction, that fraction is 2 over 3. So all of these things we should be able to do by hand. We should know these properties, these exponential properties. We should be able to apply them in functions as needed. So all these we should be able to do by hand, but we also have that calculator there to help us. Now, some of these concepts are going to be useful when it comes into terms of graphing exponential functions, and that's what we're going to focus on today. So in order to graph exponential functions here, first I want you guys to go ahead and create a table of values for f of x, which is 2 to the x power, and g of x, which is 4 to the x power. So you can create a table similar to this one. We'll go with x values -3 to +3. So create this table and then take a look at what those points look like on a graph. I'll go ahead and pause the video. Go ahead and pause the video until you complete that. So hopefully your table looks like this. I went ahead and put my numbers as fractions, and you may have decimals, but something similar to this. So what we're going to do here is we're going to go ahead and plot some of these functions. I'm going to do f of x and do f of x in blue. So I'll just put a little blue mark under this to show that f of x is going to be blue here. So -3 1/8, that's going to be kind of hard to draw, but 1/8 will be very close to the x-axis. -2 1/4 gets a little further away from the x-axis. -1 1/2 is in between 0 and 1. 0 is 1 for x. When x is 0, y is 1. Then I have 1, 2. Then I have 2, 4. And then I have 3, 8. So what we can see here is there's a path, kind of a curve that's starting to form. And we can connect the dots, and we can see that this curve is going to start to grow. It's going to increase at a faster and faster rate, and the graph is going to look something like this. So f of x was 2 to the x power. Now, if we carry this back to the left as well, it's getting closer and closer and closer to the x-axis, but it's actually never going to cross that x-axis. And so if you remember back to rational functions, this is what we call an asymptote. So at the line y equals 0, the line y equals 0, which is the x-axis, there's an asymptote. So as we go further and further and further to the left, we get closer and closer and closer to this line, y equals 0, but we do not cross it. Now let's take a look at how g of x compares to f of x. So g of x is a similar function, but instead of 2 to the x power, it's 4 to the x power. So the base, that number 2 and 4, is known as the base. The base has changed. So when I take a look at -3, it's like 1 over 64. So this is so close to the x-axis that I couldn't really draw an accurate point there. -2 is 1 over 16. That's, again, so close. It's be very tough to draw an accurate point. The -1 is 1/4. And then I have 0, 1. That point matched up between f of x and g of x. Then I have the point 1, 4, and the point 2, 16, which would be off my graph, and the point 3, 64, which would be off my graph as well. So if I draw this point in, what we're seeing here is that this graph is a similar shape, but its curve upward, its upward curvature increases at a much more rapid rate. This is what we call a growth rate. So it still has that same horizontal asymptote. It still comes close to the x-axis without crossing it. And this time as it increases at a faster rate. So we see that these curves are very similar. They have some point that's exactly the same. 0, 1. This is what we would kind of refer to as the origination point. Or if you think about a parabola, this is kind of like the vertex of the parabola. Then the base, the 2 and the 4, has been changed. And the difference we see there is that the second graph, g of x, increases at a much more rapid rate. This base, b, let's call this b again. Remember, this is from the form f of x equals b to the x. This base b, in this case, is greater than 1. What this creates is a curve that goes upward, or what we know as an exponential growth. And so what we can see here is as b increases, the curve is going to increase at a more rapid rate. If we made maybe an h of x as 6 to the x power, or 8 to the x power, or 10 to the x power, it's going to be increasing even faster than g of x. And so what we see here is an example of exponential growth. Now let's go ahead and take a look at a couple other graphs. Let's look at f of x that is 1/2 of x, and g of x that is 4 to the negative x power. So with the same table of values, see if you can graph f of x and g of x by filling out the table and then, sketching in the graphs on the coordinate plane. Okay, so hopefully you have some table of values that look like what I have up here on the screen, and you have two graphs that look like what I have up here on the screen. So notice a couple things that have changed here. Now, f of x was the reciprocal of the base that we saw in problem 2. So we had, in problem 2, we had f of x that was 2x to the x power, and now we have 1/2 x to the power, x power. What we can see here is that the values on the table are the same, but they have actually switched now. So we still have a vertical asymptote on the graph of y equals 0. But instead of this curve getting bigger as we go from right or left to right, this curve is now coming down and it's approaching the horizontal asymptote. The rate of change has stayed the same. So we see the same y values, but now the 8, 4, 2 is on the negative side, and the 1/2, 1/4, 1/8 is on the positive side in comparison to 2 that switched. So what we see here is actually b, when it is between 0 and 1, it's a fraction. It is the reciprocal of what we saw previously. When we see b that is between 0 and 1, we see an exponential decay. The graph is reducing as we go from left to right. Now, take a look at g of x. G of x has a base that is greater than 1. So we might think that, okay, this is going to be exponential growth. But if I look at the graph of g of x, it's also exponential decay. Remember what this negative does. So this negative does a couple of things, but to the base, if we were to take the negative of the base, it would actually take the reciprocal of 4. And so g of x can also be written as 1/4 to the x power. Also remember what this negative value here does. This negative value inside a function operation, if we think back to the beginning of the year in transformations, is a reflection across the x-axis, a horizontal reflection. And so if I compare g of x and f of x from number 2 to g of x and f of x from numbers 3, we can see that those are horizontal reflections of one another. And this actually brings us into the next point of graphing. All of our functions for exponential functions are going to fall under this form. And we may see some of these familiar values from earlier this year. F of x is equal to a times the base b to the x minus h power plus k. Each of these variables other than b, remember b is just the base, but it's going to contribute to the graph. But each of these other variables, I guess again, x as well, x is your input value, A, H, and K are all transformations. So we may remember the multiplication of a function can create a vertical dilation. We also may remember that if A is negative, it can create a vertical reflection, a reflection across the x-axis. B, we just denoted, B is the exponential growth or decay rate. So when B is greater than 1, it's growth. When it's between 0 and 1, it's decay. H, you may remember, is a horizontal transformation. And K, sorry, H is a horizontal translation, or let's just call that a horizontal shift. And K is a vertical shift. So what we see here are some common variables that we saw previous to this unit, earlier this year in Algebra 2, that are going to apply when graphing. So if I take a look at problem 4, take a look at problem 4a and 4b, now I have some different pieces thrown into my function, not just a base and a variable. Now I have a base, a variable, and some additions, subtractions, some multiplications in some cases. So one thing that we knew was common about, there's two things that were common about these graphs that we saw here in problem 3 and problem 4. The first thing is that they had the horizontal asymptote of y equals 0, the x-axis. The second thing they had in common, each graph had the point 0, 1. Now this is prior to transformations. So what I have here in problem 4 is, if I look here, B, this is my base. So this is B, it's my base. So I have a exponential growth here. It is greater than 1. 2 is my vertical shift. So we know that's going to shift up 2. And 1 is my horizontal shift. We know that that's going to shift to the left 1. Remember, x minus h is the generic form. So this will shift left 1. So I've got a vertical shift and I have a horizontal shift on a graph with a base B. So the vertical shift is going to affect everything up and down. So if my asymptote before doing any shifts was y equals 0, we saw that in our 4 previous functions, it's going to shift up to y equals 2. It's going to move up 2 places. Now, if all of the graphs initially had the point 0, 1, that point is going to be shifted up 2 as well. So it would move to 0, 3. It's also going to be shifted left to right. We have a horizontal shift, left 1. So my origination point is generally here at 0, 1. It's been shifted up 2 and left 1. Now we know that this is an exponential growth function, and there's no reflections. So we know that it's going to go up to the right, and then it's going to approach the asymptote to the left. Now to figure out where those values are, we can do this with or without a calculator. What we have to do is look at the base. So as I move from the origination point, the base is going to tell us how far to move up from the asymptote. So for example, if I move to the right 1, I'm going to move up from the asymptote 3 to the first power, which is 3 units. So this is 3 units above the asymptote. If I move over another line, this is going to be 3 to the second power above the asymptote. So this would be 9 units above the asymptote, which goes a little bit off of our graph, but that's okay. If I move over another line, this would be 3 to the third units above the asymptote. So 27 total units above the asymptote. If I go to my origination point, this is technically 3 to the 0 power, 1 unit above the asymptote. If I go to the left 1, this would be 3 to the negative first power, or 1/3 unit above the asymptote. And then as I go further, another line over to the left of the origination point would be 3 to the negative second power, or 1/9 unit above the asymptote. Almost so close that I could hardly sketch it in there. Then I would be 3 to the negative 1/3 or 1/27th, which is so close to that asymptote. And it's going to get closer and closer as we go. So we can sketch in this curve through the points that we have on our graph. We can also graph these with a graphing calculator. So if I were to go to my graphing calculator and clear out everything that is listed, I could type in this new function and then take a look at my graph. And here we see the function to the left. It's approaching that horizontal asymptote. And then we have that exponential growth that we see here in the picture. If I go ahead and take a look at the table, I can see some of the points that I've plotted. So we plotted negative 2 to the 2 point, or sorry, negative 2, 2.3. We plotted that right here. We have negative 1, 3. We plotted that. We have 0, 5. We have 1, 11. And then the points to the right of that would have been off the graph. So we can use the transformations to help us to graph the functions, but we can also use our graphing calculator. The next thing that it's going to ask for is domain and range. So the domain of this function is the x values. So the domain, we can see that this function is going to go to the left forever and to the right forever. So the domain is all real numbers. The range of this function would be the y values that it covers. And we can see that it is above the asymptote here, so it's greater than 2. And as we remember, what an asymptote does is it gets closer and closer and closer and closer to 2, but it never intersects 2. So y is going to be greater than 2. Never equal to, but greater than 2. So here we have a graph that we have approached in two different ways, through the transformations and through the calculator. If I take a look at problem B here, I have a base that is 1/4. And so this is an exponential decay. I have a horizontal shift. This would go to the right 2. And I have a vertical shift. This would go down 3. So if I'm going to graph this, the vertical shift is going to affect my horizontal asymptote. The horizontal shift kind of affects the horizontal asymptote, but it's a line, so that's not really going to change the line. It's going to move left to right forever regardless. So I'm going to graph this line in here, this dashed line for my horizontal asymptote. That's y equals -3. Now that point, again, all of these graphs have an origination point that starts at 0, 1 before transformations. So I'm going to start here, get this marker. I'm going to start here at 0, 1. I'm going to shift that down 3 and to the right 2. And now I have my new origination point for the graph. Now this is an exponential decay. So to the right, it's going to get closer and closer to my horizontal asymptote. To the left, it's going to get further and further away. So if I go to the right one, this would be 1/4 to the first power, which would be 1/4. And if I go, 1/4 unit from the horizontal asymptote. If I go to the right another line, if I move over another line to the right, this would be 1/4 to the 1/4 to the second power, which would be 1/8. And then 1/16 would be the next line over, and so on and so forth. So we're approaching the asymptote over here to the right. To the left of my origination point, this is technically 1/4 to the 0 power, my base. Then I would have 1/4 going left here to the negative first power. 1/4 to the negative first power is 4. So this would be 4 units above my asymptote. Then I would move over another one. This would be 1/4 to the negative second power, or 16. So 16 units above my asymptote, and that's going to go way off my graph. I'll just sketch it up here. And this is what my graph would look like. So then I can draw my curve in through the points that I have, and now I have my exponential graph here. So again, this one is an exponential decay because that b value is between 0 and 1. So let me go ahead and input this into the calculator. And we can take a look at graphing this using the calculator. And I can take a look at the graph here. This picture does kind of represent what we have shown. And I can look at the table and see that I have the point 0, 14, which we sketched up here. I have the point, sorry, I counted I forgot to change this. There you go, this should be -3. So I have the point 0, 13, sorry, there we go, 0, 13, which we sketched up here. I have the point 1, 1, which we sketched there. I have the point 2, -2. I have the point 3, -2.75, and so on and so forth. So here we have our exponential decay graph. The domain, the domain is the same as it was before. We can see that x exists within all real numbers, and this is going to be common for graphs of exponential functions. The range, it's going to be, in this case, it is above the horizontal asymptote. The range is going to be greater than -3. Now, this is going to be the case for all exponential graphs unless they have a vertical reflection. So if I had a vertical reflection, I'll go ahead and show that on the graphing calculator. So a negative out in front, you can see that my graph, in this case, the horizontal asymptote is the same horizontal asymptote we've shown below, but now it's below, or the same horizontal asymptote we've shown in B, but now it's below the horizontal asymptote. So the graph is either going to be either above or below the horizontal asymptote, but the domain is always going to be all real numbers. It's always going to go from left to go to the left forever and go to the right forever. So here we see a couple of different ways that we can graph exponential functions. We can look at using the transformations to graph those, as well as putting them into the calculator. This is a good place to stop for today. As we continue with our lessons on exponential functions, we will continue taking a look at some graphing and then get into solving. As always, thank you guys for tuning in, and I'll see you soon.